All right, so I'm Shamya. I'm a doctoral student with Professor Ryan Baker at the University of Pennsylvania at the Penn Center for Learning Analytics. This is a research in collaboration with folks at Florida State University and also UC Boulder, Colorado. Um, This is the link to the paper, and I'll be skipping over a lot of details and information that is probably needed to understand this work in a better way. So I would direct you to this link, which is this tiny.cc/quit_predict, and that basically has the paper which has all the information you would need. All right, so quit prediction. So what is our goal with quit prediction? We are trying to see if we can detect when a student is likely to give up and quit a level that he or she is working on in a learning game. And why is it important? So the grant that is funding this research is our overall goal is to see if we can sort of develop the suite of cognitive and affective supports. And when we are doing that, the immediate question you would ask is, what is the right time to give this support? Like what is it's called, in the literature sometimes it's called assistance dilemma of when is the right time and how much of information do you give and what kind, and what kind of learners would it be useful and not. So predicting quitting in such scenario basically gives us the opportunity to sort of identify the students who are struggling and then to focus the cognitive supports in the way that it aligns with the emerging key principles and concepts in their learning. Okay, so although this is a general idea of quit prediction in learning games, I would like to sort of contextualize this work in the learning game that I'm talking about, that we have used for this paper, and that's Physics Playground. So Physics Playground is a two-dimensional game which was developed for secondary school students to practice qualitative physics. So we have concepts like energy, mass, gravity, properties of torque, and so on. So this is a quick video on one of the levels. So this is one level of the game, but pretty much the idea is the same across all the levels. And here you go.
The ball sits on the ground just below the balloon. Create a fulcrum to the right of the ball and use a lever with a falling mass. The kinetic energy of the falling mass is transferred to the ball, launching it up to the balloon.
Okay. So the idea is simple. So every level basically has a green ball and a red balloon, and there are some objects on the screen, some which are static, some which are dynamic. And the objective for the student is to draw certain agents like ramp, lever, pendulum, springboard, and so on, in a way that they can launch the ball and in a way that it touches the red balloon. So each level a student can earn a silver or a gold badge based on the number of objects they are using to solve the level. All right, so some related work. The idea of quit prediction sort of falls under this bigger umbrella of disengagement behavior in intelligent tutoring systems. So people have studied things like off-task conversations, mind wandering while reading, or things like gaming the system where a student is purposefully trying to exploit a system to get the question right or finish the learning goal in that system. And in specific context of learning games itself, people have worked on off-task behavior detection and detecting what the player's goal is when they are trying to play a game, and gaming the system in the context of learning games. Quitting behavior prediction is something that has not been done a lot, and most of the work has in this kind of a realm has mostly been with MOOCs, where people have they call it drop out or stop out and not really quit, and they generally have used techniques like social network and survival analysis from the discussion board data, or engagement and performance data in the MOOC, automatic survey interventions where based on the prediction they have made on the dropout, they intervene, and in Harvard-X they found that it actually helped sort of bring back some of the students who they originally thought had dropped out of the course. The only work that we know which has done quitting prediction in the context of intelligent tutoring system is a work by DeMello and colleagues who have looked at how they can predict quitting in reading when the students are trying to read an upcoming text. All right, so the data that we have used for modeling this quitting behavior is a data that we collected through an experiment where we had 137 students, 8th and 9th graders. We had 2 days of them playing this game for 55 minutes each. Also, there were extra, like the day 1 and day 4 were mostly like ramp up and post-test, pre-test, but the actual data that we are using is the 2 days in the middle where the students were just using the system for 55 minutes each. And so we have comprehensive log data from the game. The game sort of it's very fine-grained data, and sometimes it's like 1/30th of a second data logging that the system is doing. So we have a total of 74 levels in this game, but for the purposes of this paper, we have only focused on 34 levels of these 74 because these were the only ones where we had at least 50 students who attempted those levels. So the unit of analysis for us is an event. An event here could be of many types. It could be a level-related event where the student is trying to start a level, pause or restart a level. It could be agent creation where the student is trying to draw a ramp or trying to draw some other machines in the level itself. Or it could be play-related events where it could be things like there is a object drop, there is object collision, collapse, and so on. So these are a few things that you would need to know about the game for the paper, for this presentation, but then there's a lot more information that might help, but it's all in the paper. So I would definitely encourage you guys to go and read the paper. So one thing that we have in this game is the idea of revisits to level. So a student tries to solve a level. First of all, the student is allowed to choose any level. There is no hierarchy. We have a certain linear way in which we have the levels, but there is the student can jump across the different levels and pick whichever they want to solve. And while solving a level, if the student wants to revisit a level for many reasons, maybe the student wants to try a different agent, the same level could be solved by a ramp or a springboard, or they want to try to get a better badge, like they got a silver badge before and they want to try and see if they can solve it with fewer number of objects. So there is this idea of revisit. For the purpose of this paper, we have focused on every visit as a unique instance. So every revisit is basically, we would consider it as one visit and see whether we can predict the quitting behavior of student in that visit to a level. At the same time, the student can restart a level where all the objects would get sort of reset. So for us in a visit, there could be multiple restarts, but we still would consider it as one visit from level start to level end. All right. The first important thing in the kind of feature engineering approach that we are taking for modeling a constant like quitting behavior is feature engineering. So we have built 4 different kinds of features. The first one is student level and visit related feature where we are trying to see if we can capture what the student has been doing in that particular visit to a level, how the student has been progressing in that one visit. Then there are student and level related features, which is looking at all the previous visits to that level. Maybe it's, students used a different agent, or they had a completely different approach to solving the level with the same agent. So all the previous experiences for of the student in that particular level, which is the previous visits to this level, is what we would consider for this feature. And then we have student related feature, which is across all the levels in the game, how has the student been progressing in using physics playground? And there is level related features, which is sort of trying to characterize each level based on its level difficulty or the physics concepts which are involved in that level, or the kind of agents that could be solved, that could be used to solve the particular level. So with all these 4 different kinds of features, we have a total of 101 features across, and the way we have so of course, since it's a comprehensive log data, we aggregated the data to 60-second clips, and we have for each data record in this data basically is an aggregated 60-second record for the student's attempt in that visit to a level. So we have a total of 14,000 data points and 101 features. So model training, we have two types of models that we could have tried. So one is a level agnostic model, which is a single model that we are trying to build for all the levels in the game, and the other is the level specific model, where we have for each level we are trying to customize, or we are trying to build one specialized model for that level. So level agnostic versus level specific models. So the architecture, again, more of it is in the paper. I won't go in depth with it. It's a five-fold student cross-validation, gradient boosting, model-based feature selection, standard machine learning pipeline. So one of the things that we had to do before modeling is defining quit, like how are we going to label this data. So to sort of quickly run through this process. So as a student visits a level, the student can either get a gold or a silver badge, or the student can exit a level unsolved. So in this case, the question is, do we say label the last n seconds or x percentage of the log data that got collected for that visit as criticals 1, or do we do it for all the data of that level? And we have chosen to do it for all the data with the hope that we could, this way the model is able to identify early enough the kind of quitting behavior that the student is showing. So with this, we have a class distribution of 29% quit and 71% not quit. Results. We have one of the main things that we were interested in investigating is this idea of level specific versus level agnostic model. Which one of this is better? Because if you can think of the pros and cons, there are definitely a clear goods and bad for both of these in terms of the amount of effort you would need to train for new levels, or levels where we don't have enough data and so on. So the result is in contrary to our expectation. We were thinking that we level specific model, since it has a focused attention, like the job that it has to do, we were hoping that a level specific model would do better. But in contrary to our expectation, we see that a level agnostic model, like one model built for all the levels, in fact performs better than the individual level specific models. So when we look at the features that get selected in these two kinds of ways of building the model, we see that a level agnostic model picks up the features which are more generalizable, the features which are student related or level related, or maybe student plus level related. So trying to find generalizable characteristics of quitting for that student or for that level. Whereas the level specific models were looking at whether the student drew a particular agent at a given point in time and so on. So we improved our, we decided to go with level agnostic model. It's definitely easier for us to build a level agnostic model than having to build level specific models for every new levels that we build. So we augmented this with newer, different kinds of extra features and all that. So this is the final model we have, which has an AUC of 0.81 and an F1 of 0.51. So there's a precision recall trade-off there for us, but we are very happy with the AUC of this model to use it in the production. As you see, most of the features that get selected are in fact student related and some level related in terms of the distribution across. So the kind of features that get selected mostly look at things like past visits of the student to that level and what have the students done, whether they have quit the past visits or not, or other general game related features and like level difficulty and so on. It was also important for us to sort of not treat it as a black box which just does magic. Having a gradient boosting classifier, we decided to go with partial dependence plots to see how these features are actually interacting, or how these features are giving the predictive power to the final model. And with these plots, here are some key ideas that we have for what's happening with the interaction between the model and the features. So we see that a level in which the student has received fewer badges is more likely to be quit by the future student. So it talks about level difficulty, like a level which is inherently difficult is the level which is going to be, which is more likely to be quit by the future students. We see that a student who revisits a level shows some sort of an interest probably to sort of come back and approach the level again, is less likely to quit the level. We see that the students who are more likely to quit are the ones whose attempt is like under 2 minutes or over 5 minutes. So we see a different typology. So under 2 minutes could be students who are just trying to skip and not really trying to persist on solving the level, whereas over 5 minutes could be students who are probably wheel spinning, where they're not really understanding the concept, but they are really trying to just see if they can solve the level without understanding the concept in the level itself. So this sort of talks about the effort. And then a student who has quit more levels in the past is also the one who is more likely to quit a level in the future, showing a possible low competence and disengagement. So again, all of this is a very high level interpretation, and nowhere sort of talks about the exact mechanism of how the model works. So in conclusion, we built an automated detector for student quitting behavior. We see that a level agnostic model has a superior performance, and we definitely have limitations around the fact that this was built for one particular student population. Whether or not this is generalizable to a different demographic, a different setting is definitely a question which most of us face in most of the models we build. Also the choice of label, where we are trying to label all the data of a student's visit as quit equals 1. Are we sort of intervening the student early before even they have a chance? Of the whole idea of Professor Stevens, as he was saying, whether we are enabling opportunities or we are sort of foreclosing it. So that is definitely there for us. So I'm going to skip over that, and here are some useful links. I have a link to the data in the paper, but it's no more working because we had some IRB issues after, so we had to take that down. But there's a link to play the game itself. There's my GitHub account has the code that I have used to create the feature and the model. And please follow me on Twitter if you want to know what else I'm doing. Thank you.
Thank you so much, Shamya. That was a very rigorous and an interesting study. I wanted to ask you, so when you were defining quitting as a student, getting off task, and finally not getting off task, but like leaving the game, I was wondering if you have done any qualitative research on that to check if actually that quitting behavior was something that was actually improving meaningfulness of that learning. Mind wandering could be possibly positively related to lifelong impact of that learning, or even what they were playing, even if they didn't finish the level, was improved learning through offline consolidation or any other like aspect of learning.
Absolutely beautiful question. In fact, that's the question that research question of my next research paper that I'm writing. So that's a great question because definitely this is very quant heavy, and we are not looking at actually what's happening. And one of the challenges when we are working with interaction data, as opposed to say a text or a video or a image data, is the fact that interaction data is like this huge, like just like a tabular column of like everything that the student did at every second in the game. So we are trying to use this technique called text replace, where we are trying to have a textual representation of what a student was doing in a visit, in a way that we can do qualitative analysis on the text replace that we have. So what we are basically trying to do is we are trying to look at the type 1 and type 2 errors of the model and pick the instances. Say for instance, we're going to pick a student who has the maximum error, like our model made the maximum error for that student, has the maximum type 1 error for instance. And then we would go and look at the text replace of the student for all the level visits that was mispredicted by the model. And then we're going to do a qualitative analysis of the themes that since we have a textual information, we can have annotators, we can have iterator reliability, all of that, and sort of come up, do a coding and come up with a typology for students of like those who are quitting and either quitting and a model says not quitting, or those who are not quitting and a model says quitting, or in general about quitting behavior. We could use, we could do an extensive qualitative research on such data to understand quitting behavior, understand the model's performance better.
Thank you.